Christopher King, WX. CKWX. Let's go! Chris King. Chris King. Chris King. Chris King. Chris King. Chris King. The weather guy. Clouds roll in, I'm on the case, tracking storms at lightning pace. Radar sweep and satellite, breaking it down day or night. Pressure drops, winds start to swing. Here comes that Tennessee thing. If it's headed your way, don't you guess I'll give you calm, not a miss. Chris King. Chris King. Chris King. Chris King. Chris King. Chris King. The weather guy. Cold front marching, warm air fighting. That's how you get the booming lightning. Shower storms, maybe hail. I'll tell you straight, no tall tale. Timing matters, not the hype. Forecast tools and careful type. When it's quiet, I still explain, so you're ready when it's not just rain. Temperature, dew point, wind, and sky. Putting the Y in the forecast, that's my style. Hyper local, right where you are. From the back roads to the town square far. If it matters to southern middle Tennessee, it matters to me. Chris King. 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 The weather guy. Christopher King, WX. Keeping southern middle Tennessee safe and informed.
Good evening, everyone. Welcome to a very special edition. Looks like I'm in the dark a little bit. Very special edition of uh Severe Weather Awareness Week, where I wanted to take a little bit of time and talk to you guys about severe thunderstorms, how they develop, and what kind of ingredients that we need for it, and a little bit, I guess, to help you all as you prepare for this severe weather season, some things that you can just kind of listen, take note of. Because I think knowledge is power, and I'm not the holder of all the information. In fact, I'm sure I don't have all the information for sure, but impart a little bit of wisdom over the years of experience. And now that I've been taking classes, not that I couldn't do it beforehand, I just felt like now I'm kind of bona fide and able to be able to talk to you about that. So yeah, we're gonna get right into it. It's gonna feel like a little bit of a presentation at times, but I just want to take you through all of these things that kind of come together. And so before we actually get started into the presentation, how interesting, or I don't even know if irony is the word here to describe the situation, but just as we're sitting here talking about severe weather, if I go to put over to the screen where you can see more more of the information and less of me. So, as you know, this is Severe Weather Awareness Week for the state of Tennessee. You can't hear me. My volume says I'm good. Back on and back off. I don't have any audio coming through, but my mic level says that it's good. Thank you for letting me know. I'm looking at my end going, it sounds good. If that anybody else can't, let me know. I'll be glad to uh chime in. So I'll kind of look over here to the side through my stuff. I need to be like Ron Hall for a second and go, hey, can you guys hear me before we get started? Okay. All right. So let's go ahead and get into it. So, like I said, I don't want to get into all the geeky nerdy details, but I want to give you just enough so you know that when you hear meteorologists talk about this stuff, you kind of have a better understanding of what they are mentioning. Okay. So when it comes to severe weather, the very first thing is like, what is severe weather? Okay. What severe weather to you and what severe weather to me may be a little bit different. So when I'm thinking about severe weather, I'm thinking about when a severe thunderstorm warning is issued or when a tornado warning is issued. What does all that mean? So this is really what severe weather is. This is what constitutes either as a severe thunderstorm warning or a tornado warning. So a wind speed that's 50 knots, which translates to 58 miles an hour or greater. You have to understand and I don't think I can put my presenter on. Yeah. So 58 miles an hour is because everything's really measured in knots when it comes to radar scans. So that just gets translated over, converted over to miles per hour. Hail that is 1 inch diameter or greater. So that's going to be quarter size hail. And then obviously tornadoes. Now, what you didn't see in there is what you got sitting over here on the screen, a big lightning bolt. Lightning isn't necessarily an indicator of a severe thunderstorm. Now, in severe weather safety, yes, absolutely. If you're outside and it's lightning, get the heck indoors. But to actually constitute a severe thunderstorm warning, lightning's not a part of it. Sometimes lightning can indicate when storms are a little bit more active, when there's a lot more energy in the atmosphere. But as far as being a parameter that's used to issue a warning, it's not. So that's what severe weather is. Now, really quickly, I want to talk about the ingredients that you need. Okay. So, what makes the atmosphere, what makes that setup particularly um, useful in a situation where severe weather could be present? What are the ingredients that we need? Well, here they are. These are the four things. Most people talk about three, they don't talk about wind shear, but that's kind of important. And I'm going to go into each of these in a little bit of detail. But this is what you need for severe thunderstorms, okay? You can have these for thunderstorms as well. Really, technically, I could rename this what is needed for thunderstorms. But in particular, our severe weather talk is simply this: you need instability in the atmosphere. I'm sure you've heard that word, you've heard meteorologists talk about that. You need moisture, okay? You can't have thunderstorms in dry weather. You have to have wind shear, and if you're not don't know what wind shear is, I'll explain that to you here in just a little bit. And we need lift. We've got to be able to get air to rise. That's the main thing in thunderstorms, and that's really what a lot of stuff is going to be tied to, is how well can air, and you're going to hear me use the phrase air parcel. So a parcel of air, the way I can think of it just a little cube of air. It's in the atmosphere, a molecule of it, and how easily I can get that to rise is how likely I could have severe thunderstorms. Okay. So instability, moisture, wind shear, lift. Now, before I get into all the specifics, what I have learned over the years is you have to have four of these things. You got to have all four of them. But I don't want you to get so stuck on you have to have exactly this much instability, or you have to have exactly this much moisture, or you have to have exactly this much wind shear, exactly this much lift. Those things, yes, if they're maxed out, it's going to be April 27th, 2011, and we'll kind of go in that toward the tail end of this presentation. But it's not always that maybe you have a day where the instability is low, but the wind shear is high. You can still have severe weather. So the point is that you've got to have all these present. Their amounts, well, that could depend on the severity and what type of severe weather that you have. So let's go to instability. That's the big one. So instability is what you're going to hear me call CAPE. CAPE, 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 CAPE. And CAPE simply means translated is convective allowable potential energy. And so what that means is how much energy does the atmosphere have for once an air parcel gets to a certain degree. So that air is rising. When it gets to a certain part, it no longer has to work to rise. It just does it on its own naturally. It's called the level of free convection. Once it hits that mode, how fast can it accelerate? The faster the acceleration, the stronger the updrafts, the more unstable the air. CAPE is the measure of that right there. And so this is what's called a sounding map, and you're going to look at some of these toward the tail end of this presentation, because in order for us to really understand whether or not we're going to have severe weather, what type of severe weather, we have to look at the atmosphere aloft. We have to look up. We look out too, but we mainly have to look up to see what's happening above our heads. So this is May 4th, 1999. It's one of the biggest tornadoes to ever hit Oklahoma. They said wind speeds in excess of almost 300 miles an hour of this one. If you've studied tornado history, you may know this one. This is what we would call Fat Cape. And Fat Cape just means that the difference between these two lines. And so I'll go ahead and kind of tell you a little bit about that. This first line right here, where I'm kind of scrolling back and forth, this is the part of that's what we think an air partial should do. Okay. It's kind of a normalized algorithm of what a air particle would normally do when it goes into the atmosphere, when it rises. And so, long story short, you're looking at temperature right here. That's this line to the left. This would be the temperature of the air parcel. And so, this temperature to the left is called the environmental temperature. This is what actually was observed in the atmosphere. And because this temperature that is observed is a lot less than what it should have been, that's what creates that unstable atmosphere. Just keep in mind, if hot air rises and the temperature is much cooler, well, hot air is always going to continue to rise until it cools off to the temperature of the air around it. And that's what this is. This is called the equilibrium right here. It's called the EL. And so there's a lot of energy that is stored here if we can get the air to rise to that point. Okay. So you hear a lot of people talk about instability. Well, the atmosphere is unstable. It's unstable. It's unstable. We got to watch for instability. Well, here's the thing. Okay. Cape is just the amount of energy that's there. It's kind of like a loaded powder keg ready to go in this situation. And so I will say this. Okay. You're going to hear me say this a lot. Instability in Cape does not guarantee that we will have severe weather. Okay. When you hear people talk about Cape, you need to also just keep in the back of your mind when you hear me or you hear other people talk about it. You probably saw in my shot, I had Ryan Hall in the background because watching this weather. Even sometimes we can talk about Cape and that's one piece of it. But just because we have an unstable atmosphere does not mean we have thunderstorm development. And I'll explain. So again, Cape is convective allowable potential energy, and it's the energy that the air has when it can rise freely, when it no longer has to be pushed up by the atmosphere. Okay. So that's instability. That's the first thing. Well, it's one of the things you got to have, but that's the one people talk about the most. Now, the next one is moisture. Now, we'll call this dew point. Okay. So, dew point by definition is not relative humidity. Okay. Well, make sure everybody understands that. When we're talking about relative humidity, we're really talking about the ratio of the dew point to the air temp. Okay. The closer that the dew point and the air temp are, the closer we get to 100%. When it's raining and you look at your weather thermometer or whatever, and it says that the relative humidity is 100%, that simply means that the dew point and the temperature are the same degree measurement. When we have fog at the surface, that's what happens as well. So it's an absolute measure of moisture in the atmosphere. And so maybe you're going, okay, that doesn't make a lot of sense to me. The second bullet point is, I think, what drives it home. This is the temperature the air needs to be cooled to be saturated. What I mean by that is, if the dew point is 60, then that means the air temp has got to cool to 60 before you have a relative humidity of 100%. Okay. And so moisture is a driving force. It's like the fuel for storms. And so, what standard operating procedure is, you hear most people in the weather world say, if you want severe thunderstorms, you've got to have a dew point of at least 60 degrees or higher. That's usually what happens. When we get south of 60, we just don't have enough fuel for them, for the storms to be able to grow the way they need to. So you've got it right over here talking about saturation and all that. I won't get into dry or adiabatic lapse rates or moist adiabatic lapse rates, but there's a lot that has to go into how fast things cool off, both the dew point and the temperature as you go up in the atmosphere. And that's what saturation is. When something meets saturation level, that's where clouds form. So if you ever look up in the sky, just remember this. Okay, you look at this beautiful sky here. Okay, and see how low this cloud is behind me. That just means by the time the air parcel rose, cooled off, bam, right there is where the temperature and the dew point were exactly the same, and that's where the cloud develops. Okay, we call that the LCL. Okay. So anyways, you want 60 or more to act as fuel. Okay. So moisture is the second thing that you've got to have. So instability is number one, moisture is number two. The third thing is wind shear, and wind shear is probably one of the most important of the three. Oh, and let me go back. Hang on. Just because we have dew points of 60 does not necessarily mean we have thunderstorms. Okay. Just like a second ago, just because we have instability doesn't mean we have thunderstorms. Just because we have dew points of 60 does not necessarily mean that we have moisture. I mean, we have moisture for sure, but thunderstorms. Okay. Now I'll talk about wind shear. Wind shear is two things. Okay. And I want you to look at both graphics here, both at the top and at the bottom. Okay. So wind shear is when we look at what happens at the surface of the earth. Okay. And we go up in the atmosphere and we start looking at, okay, just how fast is the wind blowing? And so what you're going to notice in the first graphic right here that I'm kind of outlining, you're noticing that the longer the arrow, the faster the speed. Okay. And so what you're noticing here is that all the lines are pointing in the same direction. We'll get to that in just a minute. But you'll notice that at the surface, it's a little bit shorter of an arrow, and the higher up you go, it gets bigger or longer. That means that with altitude, as you go up in the atmosphere, the wind speeds are picking up. And that's something that tend to naturally happen because the closer you are to the surface of the earth, whether you realize it or not, wind is affected by the friction of the earth. Okay, so when you have winds low down toward the surface, they should be a little bit slower because of the friction. It slows them down. Okay, something we all learned back in elementary school. And so we say this has wind shear because it is increasing. The speeds are increasing with height. So in this particular situation, we have speeds increasing with height, but they're all pointed in the same direction. So wind shear can also tell us the kind of severe weather that we're going to have. I can tell you based off the top picture, if all the ingredients came together as forecasted that day, this would be a severe wind event, not a tornadic event, because all of this wind is pushing in one direction. That's typically what in a worst case scenario, if you've ever heard a derecho, where you have a really prolonged, severe thunderstorm moving through with wind speeds. You may have never heard of God, I can't even think now. There's like different types of severe thunderstorm warnings. You have a considerable thunderstorm warning. You have a destructive thunderstorm warning. You actually have a PDS tornado warning. I mean, a severe thunderstorm warning. That actually, we've never had them here, but other parts of the U.S. have had those when you're dealing with straight line winds of almost 80 to 90 miles an hour. And so that would be this kind of setup here. So the speed is increasing with height, but the direction isn't changing. Now, look at the second image here. Okay. You're going to notice quite a bit of difference. If you look at the surface here, we will call this the surface. If we're going to say north and then west would be to the left and then east would be to the right exactly, maybe this is blowing, not blowing to. Remember, when we talk about wind direction, it's where it's coming from, not where it's going to. So we would say that the wind is blowing from the southeast, okay? And then you're going to notice how it blows from the southeast, then it blows from the southeast. Now it's blowing from the south, almost like southwest, almost west southwest. You're noticing that the direction of the wind is changing, but also look at the height. As it's going up into the atmosphere, it's also increasing. This would be a tornado setup. Kind of makes sense, right? You've got all these winds that are kind of swirling as they go higher and higher and higher. So that would be wind shear, talking about a change in direction as well as speed. So you can just do speed alone, or you can do speed and direction. Okay. And so the area of focus that really meteorologists want to look at is from the surface up till 6 kilometers. And from that distance, okay, that altitude, you can get a lot of information about, number one, what type of severe weather you're going to have, and also, too, just how prolonged. Like right now, if I turn back, of course, you can't see it because I'm not on screen, but if I were to take a second and come back to you and speak for a second and look back at Ryan Hall talking about a bunch of stuff, and he's been on for like 4 or 5 hours, okay? Why is that? It's because the wind shear that I was just talking about has been significant in those areas. And when there is significant in those areas, that's how you have prolonged supercells. They live in the environment. You know those ones that go across a state or two, and they drop a tornado here, and then they'll re-energize and then drop another tornado there. That's exactly what's going on up into Illinois and Indiana right now. So wind shear to me is one of the biggest ingredients that can determine like longevity of a severe system, and as well as what type. Okay. So I just want to kind of show you that and explain, to me, that this is one of the biggest things. So wind shear. And I'm going to say this before I move to the next one. Just because I have wind shear does not mean that I have severe weather. It just doesn't. I could have all the ingredients and have the wind shear, but it's the next thing that I've got to have in order for any severe thunderstorms to form, and that's lift. Okay. So lift is something that is happening at surface level that is making air rise. See, air doesn't want to tend to rise naturally, even though we do have warm air, but when you think about the surface, it's kind of warm. Things kind of stay there. So in order for us to have lift to take this air and make it rise, we have to have some things like you probably heard, like fronts, frontal boundaries, outflow boundaries, cold fronts. That's the trigger needed for thunderstorm development. So if I take let me move myself out of the way for a second. A lot of those storms develop north of the low pressure system, this warm front right here, which doesn't always happen. But the reason being is there is something called convergence. Okay. And so, if I could just take a second to kind of explain what's going on, what ends up happening is you've got a lot of air. Let me see if I can use, hang on a minute. Oh, that's perfect. Let's use green. Why not? So basically what's happening is you've got air that's kind of converging along this point like this. Okay? It's so the air kind of gets turned a little bit when it's hitting right here. And you've got some other, it depends on which way the wind's blowing, but let's just assume that the wind, because this thing is kind of moving in this general direction, we're going to assume that the wind's blowing this way. And probably what's going to happen, let me erase this a minute. That's kind of got messy. What's going to happen is you typically have this wind that is coming from the south and probably going to do this little deal right here. And you've got this wind that's going to turn like this. And so when that air converges, okay, when it comes together, when it meets, it creates lift because when there is convergence of air at the surface, what has to happen way above our head is like it's like think of it like a balance, okay? If I'm adding more air to one location, I've got to get rid of it up in the atmosphere, okay? Because just like the world, we live in an equilibrium state. So what happens is that the air aloft gets dumped. It's called divergence, happens aloft, and that's what allows that air to lift because as you're removing the air from the top, guess what's going to replace it? The air from the bottom. So that's the lift that you need. That is the trigger. You have to have that in place in order for any thunderstorm to develop. You can still have lift and not have any of the other ingredients, and maybe you'll just have a little bit of rain. But lift is that magic ingredient. It's the match. You've got to have it. Okay. So those are the things that you have to be able to have all the thunderstorm development. But guess what? All these ingredients and still thunderstorms may not form. Hey, this is the fun part of this thing. I keep going, well, guess what? It still may not form because there's one thing I have not talked to you about yet, and it's sin. Now, there's a reason I'm using this graphic. One, because I'm a Ghostbusters fan. But number two, that's Zool. Zool was the gatekeeper. And so sin, which is convective inhibition, that is the atmosphere's way of being the gatekeeper of whether or not air can rise freely. And so once it allows it to pass through, once it finds Rick Moranis, then we have definitely some severe weather. But I'm going to talk to you about what convective inhibition is. If you've ever heard somebody say the cap, the cap, the cap, the storms can't break through the cap, that's exactly what they're referring to. It's convective inhibition. So that being said, let's take a look at a very pronounced example. I know if you guys have lived in this area for any amount of time, This day, we were lucky. We were very lucky, but our friends to the south weren't so lucky. As you see a shot, this was taken April 29th, so 2 days after the fact, and you can see just how destructive these tornadoes were. So, what we're going to do is kind of just take you through a couple more instances here because we're about at the 30-minute mark. I don't have much more to talk to you about, and then I'll ask you guys if you have any questions, and we'll go from there. But I'm muted. I don't, everybody says I'm muted. I hear myself very well. Can you hear me, guys? My mic says it's on, so I'm not quite sure what the deal is. Um, and I can look and see from here. Got the right microphone on. It's saying I've got signal coming in, so I'm not quite sure. I've had this happen before. It probably when I swap something. Anyways, okay, so let's go to the April 27th outbreak. Okay, so I'm gonna click on this, and just so you know, this is a website I can share with you guys, put it in the notes or whatever. So this is what we're gonna look at is all the real stuff that was happening that day. So we're gonna look at some surface observations, and we're gonna look at some sounding maps that came from Birmingham. Okay, so just keep that in mind. So I'm gonna check out about 1 o'clock is really well. Let's start at 7 a.m. Okay. So this is what the atmosphere looked like at 7 a.m. The low pressure system that was back off here, we had a little bit of a warm front. You're going to notice the warm front doesn't look like it did in that other picture. This one looks like it's more vertical than horizontal. That's just the way things were. So we did have severe weather and even tornado warnings down here, parts of Alabama during the morning hours. But I want to show you a surface sounding of the airport there in Birmingham. So this is a sounding, and I'll take you through. You saw one just like this a minute ago. And what I want to draw attention to, I can't zoom in on this because it doesn't allow me to on this a specific site. But what I want to draw your attention to is this right here that I'm circling. Okay. All right. Let's see if I can erase that. There we go. This right here is what we call convective inhibition. Okay. It's Zool in Ghostbusters. Okay. And so what happens is that you're going to see the dew point and the temp are really close together. Okay. It's very saturated at the surface. You can see we have deep saturation, except for right here. There's a little bit of a drier layer. But what happens is as this air parcel's trying to rise, boom, it gets stuck. And what happens is now all of a sudden the temperature is actually it's actually cooler than the environmental temperature because the temperature is going to be warmer. So the result is when you hit that particular part of the atmosphere, it wants to drive the air back down. We would say it's negatively buoyant. Okay. And so that's when you say, oh, that's stable. That's very stable. That's a stable atmosphere. And so in the morning time, you're looking at Birmingham. The wind direction, yeah, it's a little crazy down low. But if I'm gonna look at that 6 kilometers, so I'm gonna look about right here, it's not turning horribly. It's not like a big turn. It is increasing a little bit with height. You can still see, man, we have a wicked jet that's above us blowing. I mean, what is that? 70, 75 knots. I mean, that's a lot, guys, at that morning time. Okay. So right now at Birmingham, they really weren't seeing anything. Okay. Just not. So what we're going to do is we're going to go to 1 p.m. Okay. We're going to fast forward. I'm going to see if I can't. I need to turn this off now. And then we're going to go to 1 p.m. There we go. Okay. And so now what we're starting to see is okay, we got a dry line right here. And that means that the dew points, if you'll just look at the dew points, 30, 51, 55, and it's 71 on the other side. So definitely you're having some storms flare up right here because you've got convergence that's happening. That's a trigger point right there. 1 p.m., stuff really hadn't started to form. We had a bunch of storms. If you'll remember that day, if you guys lived in this area, we did have a tornado touchdown in Coffee County North, right there at that Tullahoma, Moore County, Bedford County area right there as you're going up 41A. We did have a tornado touchdown that morning, but then we had a bunch of rain and then it kind of went away. Okay, so the cold front's still not there. We've got kind of a dry line in place. Storms are beginning to fire up over here in parts of Mississippi. Hasn't quite made its way to where all heck breaks loose. So let's look at a 1 p.m. and I want you to notice something already. Okay, I'm going to go back to the sounding at 7. See right here, see that cap? Boom, it's gone. Now, why is that? Okay. Now, this is something I want to tell you guys. I even heard Ron Hall say it today in meteorologists. Oh, you don't want the sun to come out. You don't want the sun to come out. You want it to stay cloudy. You don't want the sun to come out. You don't want the sun to come out. Well, let me explain why. And I'm going to go back to the 7 a.m. sounding to kind of explain it. The reason why you don't want sun to come out, because when you do, you end up warming this part of the atmosphere up. Okay. So, what I want you to do is, I want you to imagine if this is kind of the barrier, the gate. Imagine if this line and the temperature warmed up and it shifted over to the right. Okay. When it does that, it's going to look like this. And now what we start looking at is we got lots of different things going on. Number one, and I'll annotate some things over here. We have definitely got some cape here, guys. That is the cape that we're looking at. I mean, and pretty much from the get-go, there's nothing holding the air back from moving freely. And that's what's really dangerous. So do we have instability? Check. Do we have dew point? Oh my gosh, the dew point 68. Check. Okay. Wind shear. Now, here's where we can look for wind shear. It's right here, okay? And so, do you notice how the direction is changing? And I don't know if you know this or not, but to read wind barbs, each one of the long sticks is a 10, and if it's like half a stick, like right here, that's 5, and then the thing that looks like an isosceles triangle, that means 50 knots. Okay, so you're going to see it increase. Okay, 55, 60. Yeah. And so what we're looking at is right here, we do have direction of wind changing with height. So this over here is called a hodograph. And this is giving us an idea of each kilometer pretty much, and how the wind is changing it's getting the direction's changing. That's why it's veering off to the right. And it's also getting stronger because the line is going up and to the right. So do we have wind shear? Yes. Is it tornado wind shear? Yes. And then the question is, when we start getting to 1 o'clock, all we need now is the trigger. Okay. So let's go back to the surface map at 4 p.m. At this point, you've got storms that have formed right ahead of that cold front. You don't have to be right up on the cold front for the storms to form, but there's enough low-level convergence, which you've got this air from, just so you know, you've got this southerly flow, but you can't see that color. That probably doesn't work too well. You've got this southerly flow of wind that's coming in. Actually, it's more south. From the southeast, you can see all the wind barbs. See the wind barbs in their directions, but I want you to notice the wind barbs here, how they're moving. And so what's happening is you're having this convergence of air. That's what's creating the lift, in other words. And so this is nature's way of throwing the match on it. And we kind of know what happened after the fact, right? We go back to a picture that looks like what we saw just a minute ago, and just complete devastation. I mean, everything came together. And so what I want to do is I want to actually show you one more sounding before we get off of here, which is the 7 p.m. sounding. And this is where you just go gulp, because of what the hazard type says, a PDS tornado. The Cape even eroded even more. Look at the dew point at 72. The wind profile is even stronger. You can see now just how higher up that hodograph goes. And so you put all these things magically together. And again, that was the biggest outbreak I've ever seen in my lifetime. Okay. Some of you guys may be a little older than me. I'm 40. And so you guys may have been around in 70. Was it 74? The super outbreak, April 3rd, 1974, right in this area. But if you look at just the mixed layer Cape, and that's the one I look at, it gives you a better idea. It was over 3,000. Basically, that air, once it got going, it wasn't stopping, man. It was just freely going fast. And so those are the things that you have to look at that initiates the worst kind of storms. Okay. That would be in a tornado sense. Again, what would be a severe thunderstorm warning? Well, probably some of these things would still exist, but this wind profile would look completely different than it looks now. It wouldn't change direction with height, it would be in one direction. And that would give you an idea of the difference between the two. So, I took a little bit longer than I always do, but I appreciate you guys kind of sticking with me. Let me double check, make sure good. Yeah, everything's on. My mic's on. So that's kind of really it. That's all the ingredients that you need, and you can see a classic case of how all that comes together. So again, you need instability, you need moisture, you need a dew point of 60. You got to have wind shear. You've got to have it changing with direction or changing speed, and or both. And then, of course, you have to have that lifting mechanism. And then, of course, the cap can also prevent that from happening. We've had days where things have set up and looked great, but the cap was so strong, it didn't get eroded. It didn't weaken. And so the storms tried to initiate and basically hit a ceiling is basically what the cap is. It just hits a ceiling. It can't, oops, as I hit my mic there, and it can't grow anymore. And so those are the days where sometimes we've had days where we've had projected severe weather and it fell flat. That can happen. Sometimes when we have the rain, and this is in April 27th, one of our main things was for us was all that rain that came through. We had morning convection. We had rain and thunderstorms all the way till about noon, 1 o'clock in the morning. I mean, in the afternoon. And that rain, what it does is that it eliminates CAPE. Okay. Think about this. If it's raining, I remember the dew point and the temperature are really close together. And so the air particles, there's just not enough of energy. It just zaps it all up. It uses it all. So it stabilizes the atmosphere. And that was our saving grace that day. The areas that had the EF4s and fives, they didn't have all that rain, or they had it early in the morning. And then while we were getting the rain up north, they were getting nothing down to the south. And so that's what re-energized that atmosphere. So, if you guys have any questions for me, I know that maybe you're like, man, I really don't know what to ask. That's a lot of information, a lot of technical stuff, but that is really all the mechanics. That's the basics of what you need to know. You dive deeper, you know a little bit about numbers, how things get measured. You learn the math behind it, which is a ton of calculus to be able to know a lot of this stuff. And then from there, you just have to look at the numbers and continue to look at, situations that arise, and you look at warned areas. One of the things I didn't really talk to you guys about in the wind shear is really going in and showing you guys some 500 millibar maps, what actually shows you the wind speeds that are aloft. Usually, if we think about 500 millibars, it's kind of the middle of the troposphere. And so if we look at 500 to the below, we can really start to see the difference of the wind temperature, wind speeds. That's what the sounding map kind of does for us. It kind of goes in there and does all that calculation for us. So, all right. I know that I have just a couple people left. I know this is, like I said, technical. And I appreciate you guys staying with me this week. Got a couple more days of severe weather awareness week. Tomorrow, we're going to be talking about really cool something that's coming to the state of Tennessee. It's called mesonettes, and the state of Tennessee is investing a lot of money in some weather data that states like Oklahoma have had it for years, and it will actually help us in times of forecasting severe weather events. So just be on the lookout for that one. And then we've got Saturday. And if you're not super busy, head out to Nashville at Trevecca University. It's 100% free. The National Weather Service is putting on their annual Severe Weather Awareness Day, and it's free. You can go up there and meet, like I think Leland Stathem's going to be there from Channel 5, Lisa Spencer from Channel 4, Katie Morgan from Channel 17, and Marcus Bagwell from Channel 2. You can meet other meteorologists that are there, get some seminars, just learn all about severe weather. So if you like any of this intrigues you, you should definitely look at that. All 100% free. So guys, thank you so much. I appreciate you all, and I hope that you guys have a great rest of your day. Bye-bye.